Have you ever just stopped to think about circles? I mean, they're literally everywhere. But what actually makes a circle? A circle. It's not just a shape, it's an idea, a rule, a single beautiful line of code. And today, we're going to decode that rule and unlock some of the amazing geometry hidden inside. So that's really the big question we're tackling, isn't it? How can one simple little rule create a shape with such perfect, unending symmetry? It seems almost magical. Well, that's the puzzle we're here to solve. Let's dive in and break down the circle's fundamental code piece by piece. All right, first things first, we need to get to the core code. You know, every single circle, whether it's a tiny dot or a whole planet, plays by the exact same set of rules. So let's unlock it. Okay, before we jump into all the X's and Y's, let's just think about it geometrically. What is a circle, really? It's just a bunch of points, but they all share one special property. Every single one of them is the exact same distance away from one single point in the middle, the center. That distance, that's the radius. And that simple rule of equal distance, well, that's the key to everything. And here it is. This is how we write that rule in the language of math. This is the standard equation of a circle. Now, it might look a little intimidating, but it's super straightforward. This bit here, x0, y0, that's just the coordinates of the center. This rho, the Greek letter rho, that's our radius. And xy, that's just any old point on the edge of the circle. But wait a second, does this look familiar to you? Because it should. It's literally the Pythagorean theorem, just wearing a clever disguise. It's just a squared plus b squared equals c squared, set up to describe that constant distance from the center to the edge. So cool, right? Now, sometimes you'll see the circle's code written like this. This is the general form. It's basically what you get if you take that standard equation, multiply everything out, and shove all the terms over to one side. It looks a bit messy, I know, but it's actually really useful for certain kinds of problems. The only catch is that little condition at the bottom. You have to do that quick check to make sure you're actually dealing with a circle, and not just a single point or, well, nothing at all. Okay, so we've got the code. Now the fun part begins. Let's put on our detective hats because we're going to use this equation as our main tool to solve a few puzzles. We'll try to find a specific circle using just a handful of clues. All right, puzzle number one. Let's start with a nice, straightforward one. Imagine you know the exact location of a circle's center, and you also know the coordinates of one single point that sits right on its edge. How do you figure out the whole equation? Well, the solution here is just beautiful in its simplicity. We know the center, so the only thing we're missing for our equation is the radius, right? And what is the radius? It's just the distance from the center to any point on the edge. So all we have to do is calculate the distance between our known center, k, and our known point, a. That number is our radius, rho. We plug that into our standard equation and boom, puzzle solved. Okay, you ready to level up? Puzzle number two. This time, we know the center again, but instead of a point on the circle, we're given a line that just barely kisses the edge, a tangent line. Now what do we do? Once again, it all comes back to finding that radius. There's a really important rule in geometry. A radius and a tangent line always meet at a perfect right angle. Always. That means the radius represents the shortest possible path from the center to that line. So we just need to calculate that perpendicular distance. Once we have that number, we found our radius and we're good to go. And now for the big one, the classic challenge. This time, we know nothing. No center, no radius. All we have are 3 random points, and we're told that our circle has to pass through every single one of them. How on earth do we even begin to figure this out? This puzzle has such a cool, elegant solution. Just think about it. The center of the circle has to be the exact same distance from all 3 points, right? So let's take 2 of the points, A and B. Any point that's equally distant from both of them has to lie on a specific line, the perpendicular bisector. Now let's do the same thing for points B and C. Their center also has to lie on their perpendicular bisector. So where do those 2 lines cross? That single intersection point is the only spot in the entire plane that's equidistant from A, B, and C. That has to be our center. So, we know what a circle is, and we figured out how to find it. Now let's see how a circle plays with others. We're going to explore how it relates to everything around it, points, lines, and even other circles. Let's start simple, with a single point. How can you tell if it's inside, outside, or on a circle? It's just a simple comparison. First, you find the distance from the center of the circle, k, to your point, A. Then you just compare that distance to the radius. Is it smaller than the radius? The point's inside. Is it bigger? It's outside. And if it's exactly the same, bam, you've landed right on the edge. And guess what? It's the exact same idea for a line. You find the shortest distance from the center, k, to the line, which we're calling epsilon here. If that shortest distance is less than the radius, the line has to be slicing right through the circle in two places. We call that a secant line. If the distance is greater than the radius, the line misses the circle completely. And if it's exactly equal, you guessed it, we've got ourselves a tangent. Okay, so what happens when two circles meet? There are basically 5 ways it can all go down, and it all depends on one simple comparison: the distance between their centers, which we'll call delta, versus their radii, r and rho. So if the distance between the centers is bigger than the 2 radii added together, well, they're just floating apart. If that distance is exactly the sum of the radii, they touch perfectly at one single point. Then, as they get closer, they start to overlap and intersect at 2 points. This same logic just keeps going, defining every possible relationship, all with just a few simple checks. All right, for our last section, we're going to tackle something a little more advanced. But trust me, the payoff is this incredibly surprising and beautiful connection that's hidden deep inside the circle's geometry. So picture this. You have a circle, and you've got a point just hanging out in space, somewhere outside of it. From that one point, you can draw exactly 2 lines that are perfectly tangent to the circle. Now, think about the straight line that connects those 2 tangent points. You'd think the equation for that line would be a total mess to figure out, right? Well, this line has a special name. It's called the polar line. And get this, its equation is shockingly beautifully simple. For a circle centered at the origin, the equation is just this. I mean, look at that. It's so clean and elegant. It looks almost identical to the equation for a tangent line at a point that's actually on the circle. So how in the world does that work? The logic behind it is just genius. It turns out that the coordinates of both of those tangent points, B and C, magically satisfy this one single equation. And since you only need 2 points to define one unique straight line, well, this has to be the equation for the line that connects them. It's just a beautiful little piece of mathematical deduction. So there you have it. We started with a simple rule, a set of points all the same distance from the center, and from that we unlocked an entire world of puzzles, relationships, and these really elegant connections like the polar line. It really makes you wonder, doesn't it? What other amazing patterns are just hiding out there in the world of math, waiting to be decoded?